Okay, it's time to start. Let's jump right into it here. You guys have a good day yesterday? If you were able to review any of the slides from yesterday, or did you have any questions that kind of came up as you thought about what we talked about yesterday?
No.
Nope. Okay. All right. Well, let me share my screen here and we'll talk about soil formation. Okay, soil formation. So I think I've talked about this maybe the other day, the first day that we had class, but normally we kind of lump soil science into one of 5 different categories. Pedology, this is the study of soil genesis, and morphology, so how things look and how they developed. And then what falls into that also is classification. And what that is it's a system of taxonomy where we kind of give names to soils based on how they form horizons. And we're going to talk about that in the coming days quite a bit. Soil chemistry, this is the mineral composition and the reactions that happen in the soil. And this leads to things like negative charges. It informs us a little bit about water holding because the structure of the minerals tells us how well they hold water and other chemicals. So that's what chemistry is. Biology, of course, is where we study the living organisms in the soil. So it could be anything from fungi to bacteria, nematodes, actinomycetes, and even, animals, things like worms and whatnot. Soil physics, for the purpose of this class, we're kind of focus on how water moves in the soil. And, it can go beyond that. Soil physics tells us how fast things move through the soil. But we're going to mostly focus on water and how it moves through the soil. And then lastly, and most importantly of all, is soil fertility, right? This is where we're going to study plant nutrition and the things that make our plants grow and grow well. So that'll be exciting, but we have to wait till the end of the class to get to that so we can kind of lay a foundation for it. Okay, first of all, pedology. This is the study of a pedon. And we'll talk more about that in just a minute. But included in this, we're going to talk about soil genesis. How do we get from a rock to a soil? And soil morphology. So again, this is the formation of horizons and how the soil appears as you kind of move down a soil profile. You guys seen this before? I think we saw it yesterday, right? Where we talked about mineral soils, whether they weather in place or if they're transported in some form, either by wind or water. And we kind of broke them out by an alluvial deposit, aeolian, which is a wind-driven deposit, glacial, and then gravity is what we called colluvium. Okay, so keep that in mind. One of the things that I wanted to focus on today a little bit is how organic soils develop. Now, I need to make something perfectly clear here. In our society anymore, when we talk about organic this, organic that, a lot of the times it means that it's made or produced or something without, chemicals or things like that. Well, in the world of science and chemistry, when we say that something is organic, we mean that it's carbon-based. Okay, so an organic soil is one that's formed because there's a lot of organic matter in it, which is carbon-based. You and I, most living things are carbon-based. And so we get areas that, maybe has a waterway with a channel in it where the water slows down, and you start seeing things like cattails and that pop up. There could be areas of marshes and lakes. And what these things do is generally where you have water, you have plant growth, right? And where you have plant growth, the plants die off, their bodies fall to the ground, decompose, and then contribute to an organic soil. And so this kind of brings up an idea that's called ecological succession. And as I kind of explained it, right, we have water, we have an area of soil, it dies. And so you kind of see that succession in the lifespan of a plant. Those plants die, they return to the earth, they help other plants to grow by being recycled in their nutrients. And that's what ecological succession is we've got, one thing after another that ends up leading to an organic soil. And if you look at around the world, the areas where we have different soils has a lot to do with the climate. Okay, so let me. These red areas. What do you think this is? What's in the middle of Africa?
It's like the deserts, no?
I
Yeah.
think they do have a red soil.
Yeah, right, exactly. So this is desert. There's a lot of Australia is, covered in desert. The American West, a lot of it is desert. Anyway, these areas where we get desert, they tend to have very low organic matter. And it's hard to see on the screen, but if you look down here, that's what we call an aeridic soil. It's arid, okay, or dry. And again, that's because of the climate. We get areas where, let's see, what's this? I can't even read those. It's kind of fuzzy. But really, what we're seeing here is different moisture regimes. Okay, the American East, very wet. Amazon River Basin, very wet. Central Africa, wet. And so we're going to expect the soils there to be quite a bit different than anywhere else. Now, there's really two big drivers when we get an organic soil. Number one, we have to have a rate of plant growth that is greater than decomposition. And when we have this, that's when organic soils form. So if I could for a second, go back. In areas where it's really dry and hot, those are like hotbeds for plant decomposition, okay? If we were to go here and let's say we took a handful of hay or something and let it sit on the ground, it would decompose very, very quickly. And so as a result, these soils tend to not have a lot of organic matter in them. Okay, arid west, this area of Africa, Australia. Okay, and the reason is the plants are decomposing faster than they're growing. So a few things that influence plant growth. Number one, we've got to have a lot of water. And then two, we've got to have a slow rate of breakdown. And slow breakdown is generally because it's either cold or the microorganisms aren't there helping to break down. So we tend to see areas with high organic matter, they'll be wet and cold, okay? If it's wet and hot, a lot of the times the heat will help break down that organic matter and you don't have nearly the buildup. Or if it's cold and dry, there's not that water there to help the plants grow. And so can you kind of see the relationship between those two things? Temperature and moisture are the huge drivers in organic soil development. Any questions so far? Okay. So this unit right here is what we call a pedon, okay? And generally a pedon is about a meter deep, and you can see it's three-dimensional, right? So if we were to go out somewhere in the middle of a field and take a backhoe and dig a meter by a meter by a meter by a meter by a meter deep, this is going to be what we're end up with, and that's called a pedon. Okay. And as these pedons exist, they generally have different layers to them. And what we're looking at, this O right here, we're going to learn a bunch about this in the near future. But for right now, all you need to know is that this is an organic soil. Okay. And so we move down this profile, and eventually we get to a level that's called C. And this is where we get into mineral parent material. So we've got parent material up here, and basically up here is all organic matter. So it's plant material that's in various states of breaking down. And what you look at here, see, this is organic carbon, right? Okay, carbon-based organic. So as you move down the soil profile, we've got a lot of it, right? 90, almost 100% is organic matter. And then what happens when we hit the C horizon? Look at what happens to our organic carbon. It drops off. And the reason for that is that this is mineral parent material. So it's like the rocky stuff, cobbly. Okay, does that make sense? The other thing that we can look at, and we're going to talk about later, is bulk density. Bulk density basically tells us how much something weighs in a given volume. And organic matter doesn't weigh very much. And so really light, really light, really light. And then once we head into this parent material, which is rock, as a you know, a function of its volume, we've got a really high weight. So that's what bulk density is. I don't know what this is. This is like a spruce forest. Okay, but let's make some inferences here, okay? So this is northern Minnesota, okay? This is like upper latitudes of the US. And we've got, you know, a lot of lush trees. Well, they don't look that lush to me, but it looks like there could be a lot of grasses and stuff up here. And in order to have this much growth, it's got to be fairly wet. So Jessica, I'm gonna put you on the spot here. If we've got an area that's wet enough to support a lot of plant growth, and Minnesota being up in the upper latitudes of the US, it's probably a little bit colder than most areas. What might you think the organic matter in this area would be? High, low, medium? What do you think?
Medium, maybe.
Okay. Yeah, I could go with that. You know, without actually taking a sample and testing it, it's hard to know. But yeah, it'd probably be medium to high, especially where we've got all these grasses and stuff down here. And if you've got wood, you know, woody stuff that's breaking down, it might bring it up into that high range. Okay. Here's another one. And this is in the San Joaquin Valley of Central California, so in the Sacramento area. And what they've done here is you can see that there's some agricultural stuff up here. And what they did is, you know, this is usually a very marshy, wet area. And they've dug these ditches, and that helps drain the fields. And let me just tell you on this one, we tend to have a lot of organic matter because it's so marshy and wet. I mean, you could see this area right here. Okay, very wet, very marshy. And these areas tend to be kind of a peat type soil. Okay, so that's that fibrous organic stuff. And then once they drain it, a lot of that organic matter gets burned off, and we get back into kind of mineral soil up here. So interesting dynamic. So Central California, it's pretty hot there, but there's enough water to support plant growth that these tend to be really high organic soils. Okay, let's talk about weathering. So now we're kind of shifting from organic soils, and we're moving back into the realm of mineral soils. Any guys ever been here? See this picture down here? You know what that is? Nope. Okay. So yesterday on one of the field trips we took, we went to Highway 17 north of Soap Lake. This is, I think these are the Lake Lenore caves. And these are really easy to get to. You can almost drive up to it, but they're kind of fun to go explore. But these are actually a really good example of mineral weathering, okay? So we've got these basalt cliffs, right? But over time, we've kind of had these caves form. And the reason that happens in our area has a lot to do with the weather, okay? These basalt formations, they tend to have like splits and breaks in areas that are a little bit porous. And what happens is you get water that goes in there, and maybe it happens in the fall or the winter, but it gets wet and it freezes and thaws and freezes and thaws. And that action of water expanding and contracting over thousands of years can create something like this. So this is an example of what we call physical weathering, okay? Where we've got an expansion and a contraction that causes cracking. And this is kind of mediated by water, but it can happen with wind and ice as well. Anyone ever been down to like the Grand Canyon, or no, the Grand Canyon's an example of water erosion, but like Bryce Canyon in southern Utah, that's where we've got those big kind of red rock formations, and it'll form like these, you can almost get a tunnel. And what's happened is over the course of billions of years, you've had soil particles that have hit against those rocks and weathered them to create these beautiful formations. Does everyone know what I'm talking about? Should we go on a field trip? Yeah, let's go on a field trip. Okay, let me get rid of that. I mean, here's one example. What do they call this? Like,
I can't see you're not
can't-
sharing.
I'm
No,
not
you're-
sharing. Okay, let me try this again. Thanks for letting me know. Yeah, something like this, right? Or let's look at delicate arch. Here we go. Yeah, so you guys have seen this before, and this is caused by physical weathering. So the action of the soil particles blowing from the wind. Okay, cool. Let's go back to the other screen. Okay, so that part of it's physical. There's also a chemical component to weathering. And there's a bunch of different ways this happens. There's hydration. And again, this is happening at like the element level. So this isn't like water eroding, but it's water being added to like a specific mineral or a compound within a rock, and that causes it to break up. We've got dissolution where things dissolve. There's acids that can hasten dissolution and break things down. Oxidation reduction, and then complexation. And you know, I don't need you to like memorize what all these things are, but just know that chemically there's a lot of different ways that a soil can weather. This is kind of an interesting one, this complexation. A lot of the times, depending on the soil and its properties, we can get formation of organic acids. And when the organic acids and the soils interact, you get some really cool things that happen. But again, that kind of breaks down the mineral structure of the soil. And I'm not saying that that's a bad thing. It's just something that happens. Okay. Now, in the late 19th century, there was a Russian guy, and I'm not even going to try to pronounce his name, Dukachayev or something. He came up with the concept that there are these soil forming factors. And if we can, if these soil forming factors are consistent from one area of the world to another, we tend to have very similar styles of soil. Okay. And I'll give you some examples of how that works. But this was really kind of formalized by a guy named Hans Jenny in the early 1940s. And he said that there's basically 5 really important soil forming factors. And these you do need to know, okay? They are parent material, topography, climate, organisms, and time, okay? And we're going to talk about each one of those. Let me go back. So parent material. This deals with what type of rock are we dealing with? Now, yesterday we talked about sedimentary stones. We talked about igneous rocks. We talked about metamorphic rocks. And, depending on how those things are formed, that ends up being our parent material, okay? And we can make the inference that if our parent materials are the same, that our soils are going to weather similarly. Now, if we were to compare something like a basalt to like a sandstone, obviously those are very different. They're different parent materials. They're going to weather at very different rates, okay? Topography, this deals with the position of the soil on the landscape. And the best way to, I don't like this display. I'm sorry, guys. Is that better? Screen's bigger now? Okay. Topography is the position of the soil in the landscape. So soils that are living on like the top of a hill, they're going to weather very differently than, let's say that you're on the bottom of a hill now. Okay. The soils down here versus up here, they're going to weather very differently. And so that's a topography effect of soil formation. Climate, you bet. If you were to take one of our soils and maybe take it down to the Amazon rainforest where it's really hot, it's really wet, it's going to weather at a rate that's much, much faster than in our colder, drier climate. Okay, so you can see a climate effect on weathering. Organisms play a role in soil weathering, and a lot of that has to do with there's some mixing that can go on because of organisms. If you have worms, the worms tend to bring areas of soil from down low and deposit them up high, and that absolutely affects the rate at which soils weather. And then the last one, and it's probably the most logical, right, is time. The longer something sits around, the more it's going to weather, or the more of a chance it's going to have to weather. Okay? Any questions on that? Hans Jenny. And we give a name to each one of these, okay? And I'm going to give you some examples of these, and hopefully they make sense. But these are really actually pretty easy to remember. You're going to have to know these, by the way. If we have different soil forming processes based on parent material, we call that a lithosequence. If there's a variation in weathering because of topography, we call that a toposequence. Climate is climosequence. Organisms or biology is a biosequence. And time is a chronosequence, so like chronology that deals with time. That's how I remember it. So yeah, let's look at some examples here. Okay. Now, what we're looking at here is different parent materials, okay? So basalt, we know what that is, right? Limestone, okay, this is formed, it's really kind of soft stuff. It's high in calcium carbonate. And then granite, super hard, right? So if everything is the same with these, let's say the biology is the same, the time is the same, the topography is the same, the climate's the same. The only thing that's different here is that we're dealing with different parent materials. We can see that they're going to start forming in different ways. Okay. Let's look at something that's pretty obvious. Let's look at organic matter. Okay. In a like a basalt system, we might have quite a bit of organic matter in the top, I don't know, foot or so. And then after that, it tanks. Okay. If it's limestone, it breaks down a little bit faster. We have a little bit more organic matter. Organic matter is a terrible example. What was I thinking? Let's look at clay. That's not a very good example either. Who made this up? This is straight out of the book. I don't even like it. Well, at any rate, you can see that in these soil horizons that form, these A's and B's and R's, there is a difference in how they form, again, based solely upon the parent material. Okay, so this is an example of a lithosequence. Okay, without looking, what might be our, we talked about a topo sequence. What might this one be? Oh, I just gave it away. We talked about a lithosequence. This is a topo sequence, okay? So again, based on the position on the landscape, so we got the top of a hill, the slope of a hill, and then the kind of the valley of a hill, we're gonna get different soil formations, okay? In the top, we've got a nice A horizon, which is topsoil, and then it goes into these other subhorizons. But look what happens on this back slope. Our A horizon, which A stands for like a topsoil, it's quite a bit thinner, right? Than up here and down here. Why do you think that might be? Manish, I haven't picked on you yet. Why do you think we'd have a really thin layer of topsoil on this slope right here compared to the bottom and the top?
It should be organic matter. No?
No, not quite. The best way I can think to describe this is gravity. Okay. So, and the way you remember is that things tend to roll downhill. Can I draw on here? Can you guys see that? Cool. Yeah. So crap tends to roll downhill, and where things aren't moving up here. Get this stupid thing out of the way. You know, there's not as much movement down here, but here we've got this slope, right? And it's causing the soil particles to move down. So the topsoil tends to stay put up here. It tends to stay put down here. And that's why we've got thick A horizon here, thinner here, and then a little bit thicker up here. That makes sense? Okay, so again, this is an example of a topo sequence. So we're getting different soil formation because of the position on the topography. Everything else is the same, right? Same parent material, it's the same time, you know, it's the same age, similar biology, similar climate. The only thing that's different, again, is this slope right here. Okay. Now here we're looking at what we call a climosequence, okay? So we've got differences here based on the climate. And what we're trying to show here is that we've got an area, let's say that's really high precipitation, and we've got an area down here that's running off. Oh, this is the same thing. You know all this drawing that I did on here? with this little squiggly lines and stuff. This is doing the same thing. Okay. And in the case I used, gravity was moving it, but water can move it as well. So this is just the same thing. So you've got a zone where you got a lot of erosion, a zone of deposition, thick A horizon, thin A horizon, and then a somewhat thicker A horizon on the top. Okay, let's move to a climo sequence. Again, everything's the same here except for the climate. And I don't know why they like Minnesota, but let's go back to Minnesota for a while. And as we move from west to east across Minnesota, we get a different climate. So what they're trying to say is that we've got kind of a grasslandy area, and then we start to get into an area where we've got maybe a little bit more life. And finally, we're moving into an area that's got more trees and stuff. And the trees are existing because of the climate, okay? And the climate is supporting different plant growth. So we've got a thick A horizon here. We're moving into a thinner one. And then look at this one. You guys remember what O stands for? That's our organic horizon. That's happening because we've got all this plant growth that's supported by the climate as it varies from west to east. So you might have more rainfall, cooler temperatures as we head east. Okay, chronosequence. This is a change based on time. Now, yesterday we talked about alluvial depositions, right? So this is when parent material gets transported with water, and specifically alluvial is in a stream, okay? And as these streams get big and small and big and small and then smaller, we talked about how they leave these different bench type areas within a stream bed, okay? Now what's interesting is we got a good example of a chronosequence. So this stuff down here was more recently deposited. And as we move up through these different alluvial fans, we get areas that are older, okay? And so up here, time has had more of an effect than down here. This is a chronosequence. Again, everything is the same except for the amount of time that these soils have had to weather. And again, we can see different, variation in what these soil horizons look like based on the amount of time. That was a lot of stuff. It's pretty heavy. How long have we been going here?
35 minutes maybe.
Yeah. Okay. Well, what you guys want to talk about this some more? Do you have any questions? Let's look at our state for a second, because I think we've got some good examples of most of these different sequences. Let's see. All right, yeah, Washington's really a pretty good example of a lot of different types of sequences that we've got. So I went to graduate school in Pullman. So let's maybe take a trip to Pullman and pay a visit to, let's go out to like some kind of random place that has let's go out here, out in the farm ground. Okay. Can you guys see this? Good. All right. So look at this. What kind of soil formation differences might we see here? Look at those 5 words. We had the lithosequence, the climosequence. What might we have here?
Topo sequence?
Precisely. Yep. And so if we were to go out here and dig some pits, and I've done this, by the way, I spent quite a bit of time in graduate school digging pits along these landscapes, and it's stark. If you dig a pit up here and stand in it, and then dig a pit down here, the horizonation that you see form is vastly different. And again, everything's the same. The time's the same. The climate's the same. The parent material is the same. The only thing that we've got different is our topography. And so this is a good example of a topo sequence. That was interesting. Which one do you guys want to do next?
Maybe one closer to here. Moses.
Let's do it. Okay. Let's do a Climo sequence. Okay. And what we're going to need to do this, well, shoot, look at the map. It almost does it for you. Okay, we're almost to Moses Lake over here. Here's Moses Lake, right? Looking at the map over here, we've got, can you see my pointer? Okay. Look how brown and dry it is, except for the irrigated stuff, right? But this is dry. And as we move over here, still pretty dry. And then it starts getting a little bit greener, right? Okay. And the change from Moses Lake to Pullman and then further this way is we've got totally different climates. All right. The parent materials tend to be the same. The biology, you get some different, trees and plants and things growing out here, but they're growing because over here we're getting about 6 inches of rain a year total. And when you get over into the Pullman Moscow area, it's closer to like 30 inches. So it's quite a difference, right? So this is a good example from Moses Lake going to like Pullman or Spokane of a Climo sequence. Again, everything's the same except for the climate. Should we look at a litho sequence? Let me pick on Freddie again. What's a litho sequence? What is that telling us? Change based on what?
The parent material.
Yep. Okay. Let's drop ourselves. We're still on. Let me zoom out a little bit, show you where we're at. Okay, so Moses Lake, Soap Lake, again moving up through Coulee City, and this highway up here. This is going to look awfully familiar to what we looked at yesterday. But look at this, basalt, right? Basalt cliffs. Now let's move up the highway a little bit. You guys ever been up to Steamboat Rock? This is what we call it. It looks like a steamboat if you're standing there. Maybe we'll go look at it. There it is. That's what they call Steamboat Rock. But look at this. We've got basalt back here, but this looks a little different, doesn't it? Let's go further up the highway and maybe drop ourselves off right here. This is not basalt. What's this? Do you guys know what this is? That's granite. Okay. So in just a few miles, right? Looking back, you can see all this basalt back here. But in just a few miles, we've moved to a completely different parent material. Okay. So close proximity to each other. They have the same climate. I don't know if they're the same age, but I kind of assume they are because they're at the surface. Biology is the same, climate's the same, topography is the same, but we're going to get very different soils over here than we are over in this basalt stuff. So yeah, great example of a litho sequence. What haven't we done yet?
The biosequence, I think.
Yeah. I don't know if I've got a good example of that. We might have to refer back to our Minnesota example for that because, I think a lot of this change in, the area from here to over here has a lot to do with the climate. But again, got to remember that climate is causing different plants to grow. Let's go visit a place over here. Yeah, look at that. A lot of trees and stuff. I wouldn't mind living there. Let's look at this part of the state. More grassy, huh? Don't repeat me, but I think the biology effect on soil formation is like the least important of all of them. But don't tell that to like a soil biologist. They'd probably disagree. Okay, I think that covers them all, right? Okay. All right. Well, yeah, that might be something to kind of pay attention to as you drive around and look at things is, you know, you're probably going to notice a lot of different like topo sequences as you drive around, but maybe pay attention to the rocks and the parent material and the climate, and keep in mind that as those things change, the weathering of the soils is going to be quite different. So, all right, that's all I've got for today. We'll pick it up again tomorrow. Is tomorrow Thursday? That's the last day of class for the week, right? So yeah, let's round up tomorrow, and we'll talk some more about soil formation and get into, I think, a little bit into horizonation. And you guys have a great day today, okay? All right. See ya.